Hello, my Calculus AB students. We are doing section 3.6. We're going to look at number 37, kind of an in-depth look with a full explanation. So this is a rate of change derivatives, this application. So the other one we did earlier, if you looked at number 13, was a position function. This is the volume situation. So let's read this. A cylindrical tank is full at t equals 0 hours. So I'm going to draw a tank. Oh, my tank is beautiful? Wow, thank you. So it's full. At times t equals 0, it's full of water. When the valve at the bottom of the tank is opened, so at the bottom we have this little valve, and water is flowing out of that valve. So that's what's happening here. Now, if you have experience with these kind of tanks, we know that when there's a lot of water on top, gravity is pulling down and the water flows really fast. But when the water level drops, there's not much gravity pulling down on the water, therefore it doesn't flow out as quickly. And so therefore it's not a linear the water doesn't leave in a linear pattern. At first it comes out faster and over time it slows down. So therefore some dude, Mr. Torricelli has a law. And according to his law, this formula gives you the amount of water in the tank at any time. So if you put in 0 here, that will be the amount of water in cubic meters when t equals 0. As you plug in new times, it'll give you the amount of water at that time. So you have to understand what this function gives you. Now we're asked to graph the volume function. Now let me put that in Desmos and show you what happens. 100, 200 minus t squared. So let's get rid of these. So we have 100 parentheses 200 minus t, I use x, squared. And then you look at this graph and like, I don't see it. Where is it? Well, we're zoomed way too in. So if I zoom out, okay, there it is. Here's my problem. It's like I can't see the left, I can't see the top. I can't see where it goes. And if I zoom out more to try to see where it goes, then it becomes yucky. So how do we solve this problem? My width, I like the width there, but I want to see the top. Well, if you look, the top on the Y is 5,000. That's not big enough. I need to go bigger. So I hit my settings. And you could do this on the TI-84 also. It's in Windows. But this is beautiful because it changes on the fly. So 5, that's 50, 5,000, 500, 5,000. That's 50,000, 500,000, 5 mil. Okay, there we go. Now I can see the graph. So I just had to change the windows. Now there is my volume. And so let me jump back to this. I've already pasted it here. And what is this graph saying? We have to be able to read this. So at time t equals 0, this is the amount of water in the tank. I can't even read that. Is that 4 million gallons? I think it's 4 million gallons, I think. Yeah, 4 million gallons. And as time goes on, the volume decreases very quickly. Look, it's dropping. But here it starts to slow down. It doesn't drop as fast. It starts to flatten out. That's because there's less gravity, and so the water doesn't flow out as quickly. And then at 200 hours, our tank is empty. And so therefore it's at 0. This part is irrelevant. Your water's not going to go back into the tank after it's gone out. Once you get to 0, it stops. You don't go back up the curve. So we can technically stop at 200 here. So our first two questions are pretty much answered, but I want to do this algebraically as well as graphically. What's the volume in a tank before the valve is opened? You see it right there. That's at t equals 0. You can measure 4 million cubic meters. So to answer this, 4 million cubic meters of water. That's a lot. And then, when is the tank empty? Part B. Well, when the volume is 0. 0 right there. So that's going to be at 200 hours. So 200 hours. And I probably didn't point that out. We're told the units are hours. Forgot to mention that. Now, how could you do this without a calculator? Well, part A, you want the volume at time 0. You're just going to put a 0 right there. It's going to be 100 times 200 squared. 200 squared is with 4 zeros, and then 2 more zeros from that, and you get 4 million cubic meters of water. Now we look at the next part. How long does it take for the tank to empty? Well, on this one, you want the volume, which is given by this function, to be 0. You set that equal to 0. Well, this is already factored. In algebra, you factor to solve an equation. And then after you factored, you set each factor equal to 0. And I'm going to remind you why. If this were to equal 0, it doesn't matter what these are. 0 times anything is 0, so thus will be 0. And then if we set this one equal to 0, well, it doesn't matter what this and this are. These are, because 0 times anything is 0. Now, can we set that equal to 0? No, because this is a constant. It's always 100. It's never 0. So that's why we set each term equal to 0. Well, clearly those two are the same. So t equals 200 is when the tank is empty, and we see that by the graph also. So that's parts A and B. Find the rate which water flows from the tank and plot the flow rate function. Well, the key word here is rate. Now, if you remember when we talked about derivatives, it's the instantaneous rate of change. And then we had something called the average rate of change. The derivative is at the instant, and the average rate of change is over a period of time, how fast something changes. So rate, for average rate of change, that's going to be change in the volume of water over change in time. How much volume is flowing? But if you want to do instantaneous rate of change, that is dv dt. It's as t approaches 0, the change in time, that's the instantaneous rate. That is the derivative. So there's a big association with these two. This is over a period of time, and instantaneous is at an instant of time. Now, this wants the rate at which water flows from the tank and plot. They want the rate at every single time. That means they want the instantaneous rate all over. Another hint, it never says average. So it's implied in this rate that it's instantaneous. It's implied they want the derivative. So v prime of t, understand what it's telling you. It's telling you the change in volume as time changes. Now, you might have another issue. If I find dv dt, that's going to give me the change in volume of what? Of the tank. How fast, or what the change in volume of the tank is. But they're asking the water flows from the tank. So here's the logic you have to have. If I know the volume of water flowing out, clearly and obviously that is the amount of water that's leaving the tank. So the rate of change of the volume in the tank is the same as the rate of change of volume coming out of the spigot. Now if we find the derivative of this, since water's leaving, volume's decreasing, therefore the derivative will be negative. But as far as the volume of water flowing out, it's opposite. Because it's flowing out, you're getting more and more water, so the rate flowing out is a positive. So just throwing that out at you. So what is v prime of t? Well, we need to take the derivative of v of t, and let me remind you what v of t is. That's 100, 200 minus t squared. Well, you actually know how to do this with the chain rule now. Well, you're supposed to. But we're just going to do it old-fashioned way. We're going to rewrite this. Now, you could do product rule, because you could see we have the product of two functions here. So product rule is a possibility, but we're not going to do product rule. There's an easier way that we're going to do. We're going to multiply all this out. If we do that, we get 40,000 minus 400t minus t, or plus t squared. And so when we take the derivative, we have the constant rule. We leave the constant. The derivative of that is 0, so we're going to get a 0 there. The derivative of that is minus 400, so we're going to get a minus 400 there. And the derivative of that is 2t, so plus 2t, 2d. So this is our v prime of t. If you want to distribute, you can. Actually, I'd rather factor things out. I like factoring. Let's take a 2 out. We'll be left with minus 200 plus t, which will give us 200 t minus 200. There is our volume formula. So that's the rate at which water flows from the tank. And technically, no. That's the rate which water leaves the tank. That's the rate of the amount of water in the tank. So really, we'd have to put a minus in front of this to make it the rate which water flows out of the tank. But I don't want to get into that right now. So if you go to Desmos and graph it, I did it already. Here is the graph of v prime of t. And so what's the question? At what time is the magnitude of the flow rate a minimum, and what time is it a maximum? So we're going to stop at 200, because we already learned that the tank is empty after 200 hours. We saw that here. After 200 hours, the tank is empty. So technically, we stop here, and we're starting here. Now you have to understand what magnitude means. Magnitude means I don't care about the plus or minus. I just want the number. Just give me the number without positives or negatives, and whichever one's the biggest has the largest magnitude, and the smallest has the smallest magnitude. Well, at this point, we can see that v prime of t is 0. And at this point, we can see that v prime of t is, I can't see, I don't know. I have to look at my function to remember what it was. Oh, where'd it go? I've lost my notes. Oh, these are them. Okay, I can do this. It's going to be negative 40,000. So if I had zoomed in on that spot, it's negative 40,000. But magnitude is absolute value. You don't care about positives and negatives. And this magnitude is still 0. So let's read the question. Rate. It wants to know when the derivative is a minimum and when it's a maximum. Well, it's a minimum at 200 hours, and the minimum value is 0. And it's a maximum at 0 hours, and the rate is 40,000 cubic meters per hour. That's the units there. I forgot to do units. I apologize. But that's the end of this question. Hopefully that's helpful. Bye-bye.